In physics, we deal a lot with coordinate systems. We deal a lot with coordinates. But coordinates aren't real physical objects. Real physical objects are quantities. They're scalars, they're vectors, and they're tensors. And so the next important thing to do is to take our idea of special relativity and put everything into tensor form. In classical mechanics, we saw that the fundamental objects were all scalars and vectors and tensors in 3 space. So your fundamental position vector might look something like this. We have 3 basis vectors in the cardinal directions in the Cartesian coordinates, and you have 3 coordinates describing how far you are along those 3 vectors. And we'd often write those vectors just as the coordinates themselves, and in fact we'd have a dual space to this vector space, and we'd write covectors, and the relationship between this vector and its covector is you'd simply have the same 3 coordinates. Now in special relativity, we've discovered that time isn't really separate from space in the same way as it is in classical mechanics. Time and space can be intermingled as you change from one reference frame to another. So our fundamental objects in special relativity actually have to be 4-dimensional. They have to be 4 vectors in space-time. And so our 4 coordinates have a time and 3 spatial dimensions. And you'll note that we have to have the speed of light attached to the time in order to get the right dimensions to make them all spatial. So this 4 vector doesn't just represent a particular place in space, it represents a particular place in space and a time. So in other words, this is an event. This is a particular thing happening in a particular place at a particular time. And so all the events that we're discussing in our previous exercises will be described in terms of 4 vectors most naturally. And because this event is a real physical thing, it has an existence outside of the coordinates we use. So if we go and rotate our spatial coordinates, or we change reference frames by moving with a constant velocity with respect to a different reference frame, we know exactly how these coordinates are going to have to change. So in terms of the spatial rotations, we're only going to change the spatial parts of the coordinates according to the normal rotation matrices. If we change reference frames by going to a different velocity, and that's called a boost, then we have to follow the Lorentz transforms. And written in that form, we can really see the linearity of our Lorentz transform emphasized. Interestingly, the Lorentz transform that's a boost, that takes us from one inertial reference frame to another one moving at a constant velocity, is actually just a rotation between a spatial coordinate and the time coordinate. It's often a lot more compact to write these kinds of matrix relationships in terms of the coordinates, and also when we start talking about tensors, it's much more easy to use coordinate type representations rather than graphical ones, because the graphical ones have to get higher and higher dimensional. So we have to talk about the components of our 4 vector. It's very common notation to use Greek letters to describe indices of 4 vectors, just as we use Latin indices to describe components of 3 vectors. And so if we have the components of our position vector in our transform coordinates, we're going to need some 2-index function to describe this matrix. And we're using the Einstein summation notation. The Einstein summation notation actually came out of 4 vectors. And so we're summing over nu here to get our components. Okay, so in other words, this matrix here, this L for the Lorentz transform, the components are defined by that matrix there. We're going to use the convention that the indices here span from 0 to 3, with the 0 index being the time index and the non-zero indices being the 3 spatial indices, x, y, and z respectively. Sometimes in other conventions people go from 1 to 4, sometimes people put the time coordinate at the end. We're going to follow this all the way through, but do watch out if you're looking through other textbooks. So we've met Euclidean space, and we've met Minkowski space now. The other vector space that we met was, of course, Hilbert space. That was a little more exciting because it came in lots more flavors rather than being strictly 3-dimensional or strictly 4-dimensional. It came in everything from 2-dimensional up to infinite dimensional. But it had a slightly different structure between its vectors and covectors. Remember, we had all our bras were covectors and all our kets were vectors. And our inner product between those two, in Einstein summation notation, would be the sum of these things. Or in matrix notation, supposing it was just 2-dimensional. In other words, to get the coefficients for the covector out of a vector in Hilbert space, we didn't just turn it from a column vector to a row vector, we also took the complex conjugate of all the coefficients. What do we have to do to get the inner product for Minkowski space? Is it as simple as the Euclidean space one? Is it just take all these numbers and arrange them in a row? Or is it a little bit more complicated than that? So the real question is, what is the inner product? And a related question is, what is the relationship between the vectors and the covectors? Now the key point here is that inner products have physical meaning. They take us from vectors to scalars. And what's a scalar? A scalar is a physical quantity that's supposed to be independent of our choice of reference frame. It's supposed to be independent of our choice of coordinates. So if we take the inner product between two vectors, it's not supposed to matter what reference frame we look at it in or what coordinates we write it down in. So what is it that we know that's completely independent of what reference frame we're in for Minkowski space? And their answer is, of course, the speed of light. So if I have something traveling at the speed of light, then that is going to be zero. And it's going to be zero in all reference frames. So that's a bit of a clue. So if this kind of thing is the same in all reference frames, then we might imagine that our inner product looks something very much like this. If we ignore the time term for a moment and we ignore these minus signs, then you can see that this bit looks exactly like the inner product for Euclidean 3 space. It's the product of the x component terms added to the product of the y component terms added to the product of the z component terms. But we do have this minus sign, and we also have the product of the time-like component terms, but you can see that there's a different sign between the time and the spatial components. And that's what we have up here, which is where we got our guess from. This notation here, this is the actual components, like that, and so this here is a matrix which is going to give us these minus signs. So it's really just this matrix, and this is called the metric. Now for special relativity, this is always the metric in Cartesian coordinates. But in general relativity, the metric can actually change, which is why we're going to keep this notation and use it throughout. Now you can check for yourself that if you apply this inner product, an inner product of this form, then if you do any rotations, you get the same answer. We're already sure about that because it's got the spatial part that looks just like the Euclidean inner product. And the Euclidean inner product doesn't change when we do spatial rotations, so we never expected that to change. And you can show, either by brute force or by being clever, that applying boosts like this, having Lorentz transforms like this, also don't change the form of this inner product. So if you calculate this in one frame, and then you go and calculate it in another frame, you always get the same number. So we can show that invariance for boosts by brute force. So I'll define my gamma, I'll define my Lorentz transform matrix, and I'll define a pair of vectors. So here's a pair of 4 vectors. This might be time, space, space, space. I'm going to define my diagonal matrix, which is my metric. And then if I take the inner product between my two vectors with my metric sandwiched in between, then I'll get the time-like components multiplied together minus the normal norm for the spatial components, the products of the x, y, and z components all added together. And now if I'm going to see whether this boost actually changes that inner product, I have to apply L to A and I have to apply L to B. And so now I'll apply L to A, I'll apply L to B, and you'll see I get exactly the same thing out. So there you go. We've shown that we get the same inner product in any reference frame. So the form of the inner product essentially tells us what to do to go from vectors to covectors. So we can write the inner product as the sum over the components of a covector. So if I write the index down, then that's going to be a covector. And if I write the index up, then that means the components of the vector. So this is just exactly this here, which means that we know what the components of the covector are. So again, we're summing over the news here, just as you summed over the muse there. Remember, any repeated index is a dummy index, so it doesn't matter what we call it. And so this is the form. We use the metric here to take an index and lower it. And we know what that does because this metric is just this matrix here. All that does is it puts a minus sign on all of the spatial-like components of this vector. So now that we've introduced all the machinery of 4 vectors, our next goal is to take all the laws of mechanics that we know and all laws of physics and convert them over into 4-vector formalism so that our laws of physics are no longer dependent on coordinates, but they're talking about the real physical quantities directly.